everything after today is the last week of classes, and we're just going to review the last week of classes. So this is the last content lectures today, the last new stuff. It'll just be review from after this lecture onward. So let's finish strong. Let's talk about some more game theory stuff. And then I want to talk to you about a different topic called recursion. That'll be awesome. So, yeah, we talked about last time this prisoner's dilemma, and it was odd that we noticed that the right thing to do, because you can't trust your other prisoner accomplice, the right thing to do is always to confess, even though that's going to give you 5 years in prison. If you were able to trust your partner, you would both just not confess and walk out of jail, but you can't expect that. The Nash equilibrium was telling us that we should confess if we were ever one of these prisoners. So let's keep going along those lines of things, and I'll talk about some other games that you can play that have been studied. So this one is very easy to understand. It's cake cutting. So you have a cake and you would like to cut it and share it evenly with people, and everybody needs to make sure that they get a fair share of their fair share of the cake. So a nice sized piece, nobody gets left out. And I tried to search for whether or not this was a cooperative game or a non-cooperative game, because like you're in a group of people trying to share this cake, so maybe it's cooperative, but maybe because of the rules that I'm about to explain, it could also be argued to be non-cooperative. But remember that cooperative means that forming alliances is a good thing. So I'm not sure. This could be a non-cooperative game. I'll leave that to you to decide. But yeah, it seems like this cooperation is kind of forced upon you. So here's the game. Maybe you played this with a sibling or something before. You have your cake. You're going to share it. And maybe your mom says you're going to share it with your sister, like I did once upon a time. So you get to cut the cake, and then the other person gets to choose which piece they want. All right, so that's the game. And so that means that you should cut the cake perfectly in half, because you're going to assume that the other person wants just as much as you. And if you cut it in half, then everybody, there's no better piece, and you can both share evenly. You can very easily lose that game, because if you cut it in a bad way, like this or something, if that's the way you cut the cake, of course, the other person who gets to choose which piece they want is going to pick the big piece, and you're going to be left with a tiny amount. So you're kind of forced to play nicely, to share. Okay, so that's the cake cutting game. Maybe you've played it yourself, or at least heard of it before. But what is the optimal strategy? I think you could argue very easily that it would be cutting the cake in half, so that you could get an equal amount and be guaranteed half the cake. So that's as most as you can guarantee for yourself, unless the other person's not hungry, I guess. That would require an alliance, maybe. So that's a potentially optimal strategy for cake cutting. Just cut it in half, which makes a lot of sense. There is a way to study what is optimal. There's a term in game theory called Pareto optimality, and I would like to talk about that. So what we're doing with cutting cake is we're like sharing things. We're allocating a resource. That's the fancy term. This is a resource allocation problem, and resource allocation is Pareto optimal when if you were to change the allocation, that would leave somebody worse off, which is very vague and like academic way of saying something. So let me try and teach you what Pareto optimal means. It's a very utilitarian idea, though. It's like changing the allocation would always leave somebody worse off. So, all right, this idea. So let's say we cut the cake in a fair way. So exactly down the middle. If we were to change the way that we cut the cake, what would happen? Would somebody be worse off? I think you can argue yes, because if you changed to cut the cake like this instead, oops, I want a different color. If you cut the cake a little bit like this instead, where there's like slightly bigger side and slightly smaller side now, then you've just made a worse, like somebody's going to get this piece over here that's now smaller. And so that means that cutting the cake in half was Pareto optimal, because changing that, cut it perfectly in half, leave somebody else worse off. Do you see that? So we can argue that, yeah, that was a good way to do it because it was Pareto optimal. So that's nice. And so that was one way to be Pareto optimal. It's asking the question, what kinds of ways of cutting the cake leave somebody worse off if you were to change it? So cutting the cake in half is totally Pareto optimal, but surprisingly, watch. Even if you cut the cake in a horrible way, if this was your cake and you cut it like this or something, in a bad way, even if you change this one, if you change this one a little bit, somebody's still worse off. You see that? The person who was going to take the big piece used to have all this, but now they get all this. So they are now worse off, which is surprising. So it just so turns out that every way that you could cut a cake is Pareto optimal. So this term is only good sometimes. It's interesting. But it is a way of determining when you have a good outcome for your game. You always want to search for Pareto optimality, but sometimes it breaks down. I should say that the reason why the prisoner's dilemma is so confusing, the reason why it doesn't make sense to our minds, is because the Nash equilibrium that we found, it's a non-Pareto optimal outcome, which is very, very weird. Because obviously, if you were to change the allocation, there's a way to make it better for everybody, but nobody's going to do that. So that's non-Pareto optimal. But still, it was the way that the prisoners should behave. And so I guess this term is a good way of at least explaining why we were scratching our heads so much when we described our prisoner's dilemma problem. That's why it's so counterintuitive. So yeah, that's Pareto optimality. Any questions about that? It's a standard term that you'll see. You can apply this to many games. All right. For my next trick, I want to show you a way to split an Uber ride for in a fair way. This is a way of playing the let's take a cab together game. It is a cooperative game, so there's like two people, and they're going to share a taxi on the way home because the first person lives on the way to the second person's house. So like here are two people, instead of person A and person B in computer science lingo, instead of that we say Alice and Bob are these two people in our example. And so here is the taxi that they call, and let's see here. It's going to take a route, and it just so happens that Alice lives right here, and Bob lives right here on the way. So Alice lives on the way to Bob's house, and so they're going to share the taxi and try and split the bill. So let's figure this out. So if Alice took the taxi by herself, she would be spending $5. It's closer. Her house is closer. And then if Bob went and got a taxi by himself, he would go and he'd pay $12 because it's a longer ride. But because Alice lives on the way and they're going to share the cab, the fare for both of them is still $12. So the question is, how much should they split the bill? What is the optimal scoring here? It's definitely not half because it would have been easier for Alice to spend $5 rather than the 12 over 2, which is 6. So what is the fair way to split the bill? And the way that you can calculate this is to use a game theoretical concept called the Shapley value that we will calculate together. So notice first of all that like $6 and $6 is absolutely not fair for Alice. It's a great deal for Bob though. That is not fair. So this is not an obvious answer for how they should share. And I wonder if Uber has this like implemented in their app, because I think you can share rides with people. So let's figure this out. And the way to calculate the Shapley value, the optimal price that Alice and Bob should pay if they're going to share, is you consider the permutations of who pays the bill first, and then the person left pays the rest. So that doesn't make a lot of sense. Let me show you an example, and hopefully it will make more sense. So the two orderings of who pays first would have been Alice or Bob, right? Alice and Bob. Alice pays first, then Bob, or Bob pays first and then Alice. And so these are the two orderings. So either Alice pays first and then Bob pays next, or Bob pays first and Alice pays next. And here's the game. So the fare is going to be $12 total. And so if Alice pays first, she's going to pay her full amount. So she would pay $5 if it worked like this. And then Bob pays what's remaining. That would have been $7. If Bob went first, he'd pay his full amount. That would be the $12 to get him all the way home. If Alice went second, if she was going to pay the rest, then she would pay $0. You see that? So these are the two orderings of who pays first. They're going to pay their full amount, and then the rest is covered by the second person. So that's how you compute this fancy number. And what you do is you take the average, and that tells you the proper price. So let's talk about this from Alice's perspective. So what is the average cost for Alice? So if we did it in this order, she would have paid $5 for the ride. And if we did it in this order, Alice would have paid $0 for the ride. And what you do is you take the average, just like we were calculating the average for the prisoner's dilemma problem to tell us which one to do. The average price across all these different possibilities is the average of 5 and 0, so $2.50. That is the fair price that Alice should pay if she's sharing this cab with Bob. Okay, it's cheaper than it would have been to take her home by herself, and Bob is also paying less. But this is apparently the fairest, for some definition of fair. The fairest fare. That's a fun phrase. Are there any questions about that? Just consider every possible ordering, and then you take the average, and that gives you a good number. That sounds kind of fair to me, at least. So next time you share an Uber with somebody, you can use this to calculate what you should pay. All right. For my last few pieces of these slides, I want to show you an algorithm called Minimax. It has a cute name. There are fun examples of it on the internet. I encourage you to watch them. But let me teach you the basic idea of this. This is a way to discover the optimal way to play certain games, one of which could be tic-tac-toe. So it's a search problem. It's an algorithm. It's used to find the optimal way to play some game like tic-tac-toe or chess or something like that. And here's how you do it. So take your current state of the game, like you have a game board, and then let's pretend like it's X's turn. What the question we want to ask is how should we move to ensure victory in the most cases? What is the optimal move for X right now? And the answer is, because this board could be anything, I think you can see the answer right now, but you can imagine that it could be harder to find. There could be many moves to make still. The question is, how do you find the best move to play? And the answer is simulate the rest of the entire game. How could it be? How could the game play out? Maybe X moves like here, or and then O moves and does stuff. Who knows? I think the game would be over at that point. But like, make X move, draw on your board, and then it's O's turn. List all the possibilities for what O could have done. And then just do this a bunch of times. Like, all right, that otherwise, if X didn't go there, maybe X went here. And then it's O's turn. And they went like this. There are just a bunch of different possibilities, and you want to list them all the ways for the game to be played until somebody wins or it's a tie, or the game's board is like full. So that's what you do. You just write it all out. Tic-tac-toe is a small enough game to be able to write out every single possibility, and then you can use this Minimax algorithm. What you do, the reason it's called Minimax, it should make sense. When it's your turn, what you do is you make the move that maximizes your chance of winning, and then when you're simulating your opponent's turn, that you're going to go and assume that they're going to make the move that minimizes your chance of winning. So in the face of their minimization, you're trying to maximize your outcome. That is how you solve for the optimal next move. And so essentially, you're assuming that your opponent is really good. So technically, Minimax could break down if your opponent was making weird moves, but we'll assume that they are trying to win, and it should give you the best outcome. So it's going to generate all these possibilities and then somehow score them and give back the best possible next move. And so here's a question for you to try. Starting here, take out a piece of paper. You don't have to write this down anywhere to share, but try and help your neighbors get it right. But starting from this game state, make a chart for all the different ways that the game could go. Pretend that it is X's turn. So fill in O's moves too if you have some time. But like here's an example of how the game could be played next. So the board was like this: X, O, 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 X, X, and it's X's turn. So it's potentially the case that X could go here. You see that? So that's one possibility. Draw out all the other possibilities for X. And then, if you have time, draw out all the possibilities for O as well. Dot, dot, dot. Because now it's O's turn to move from here. You see that? So give that a try for a couple minutes, and then I'll show you the answer and how to compute the best possible move. How Minimax does it. All right. Any questions that came up as we tried that? It's like as an example for what could happen after this one, it's like, all right, O could go somewhere now. Like the board looks like this, X, O, X, X. Then O could maybe go here. Or, of course, they could have gone here and won the game, but that's another option. You list them all. And so that's how it works. And so let me show it to you what could happen. So we got X, O, O, in the middle, X, X. So that's the initial board. I think that's still too big. I have a lot to draw. So X, O, 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 X, X. So that is the starting board. And so what are all the different ways that the game could be played? So let's see here. It's X's turn. So let's see if I can make this easier on myself. I'll copy and paste this because I got to fill it in. So could go there, could go here. There's three options for X because there's three spaces. That should work. Boop, boop, or that one. So X could go here, or here, or here. See that? And then what could happen with O? Well, there are two ways that O could play the game now. Let's see here. From here, at least. Two ways that O could play. What could they do? They could go. Shoot. Well, if it's O's turn, they could have gone here, or they could have gone here. Those are possibilities. And then we just keep going as far as we can. Like, the game's still not over yet. Like, there's still one move that X could make here, and it's the winning move. in two different ways. X, O, O, X, O, O, X, X, X. So that's nice. X wins. This game is already done. So there's no moves to make from there. This game is done, so there's no moves to make from there. But this game is still playable. So what could O do now? What are our options? Again, there are two, because there's two spaces left. So O could go either here. Oh, sorry, are there three options? Oh no, sorry. There is something happened with the X. What happened here? That is the right one. There's only two spots. I think I just didn't copy it properly. There we go. Alright, so O could go either here or here. And then it's X's turn. After that, this game is still not over. So X could go here and win the game in the last open spot. O, O, X, then X, X, X. And then this one is over because O has won the game. So you can't go any deeper than this. All the games are either over or like they're ties. The board is full. So that's a win for X, that's a win for O. This one is a win for O, this one is a win for X. So you can't go any deeper than any of those. Can't go any, there's nothing left to do. So that is the complete set of possibilities and all the ways to get there for the initial starting game board. Are there any questions about how I got that? Is that how we got it? So now let me show you how Minimax works. Again, it's trying to maximize our chance of winning. Let's pretend that we are X. It's our turn to make the move, so it's going to like simulate the game. And then we're going to assume that our opponent is good, and they're going to try and minimize our chance of winning. So we're going to try to maximize our chance in the face of them trying to minimize our chance. So let's talk about how this works. We're going to assign a score to every game board. That has to do with what's going on. So, all right. It's easier to start with the ones at the bottom where the game's over. So this board, how should we score it? We are X. We're trying to win for X. So let's give, because X won for this board, let's give this a +1 score. Like we want that one. High scores are good. So this is a +1 score because we are X and we like that. We like winning. This game, for example, this board is O winning. We don't want that because we're supposed to be X. And so we'll give this a -1 score. See that? And that's the idea. And then for anybody up above where the game's not over yet, like this one could only lead to here, what you do is you take what was below you. You take the best thing that's below you. Because like this is X's turn, so we're going to maximize the thing down here. And so this is going to be +1 again. Because it's like this leads to a win for us. So it's positive, it's good. All right? So that's that one. This one is another win for us, so +1. This one is another win for us, so +1. And that is the only move from here, so we're trying to maximize our score when it's our turn, so again, +1. This is when O wins, and so we don't like that, that's -1. And now let's talk about how we're going to score these kinds of boards, these ones up here, because there's options now. Whose turn is it right here for this board, is the question. It is O's turn, all right? And we get to assume that they're going to try and minimize our chance of winning. We're going to assume that they're the best possible player that they could be. And so we're going to assume that they're going to take the side, they're going to take the choice that leads to their best outcome. So our score involves assuming that they're going to take this move. You see that? They're trying to minimize our chances of winning. And so when it's O's turn, we look at all of our possibilities. It's the +1 and the -1. When it's O's turn, they're trying to minimize. So the score for this board, when it's O's turn, is the least possible one we could get, which is -1. You see that? That's how we're going to score that board. This one, again, it's O's turn, and they're going to try and minimize all the possibilities. So we're going to assume that they're going to take this move rather than this move. And so when it's O's turn, we assign the score that is the minimum score possible from then on. And so that's -1 again. And then now we're back here to our original board, and it's X's turn. When it's X's turn, we're going to try and get the best outcome for X. So we're going to maximize all the possibilities. This is a possibility, this is a possibility, this is a possibility. but when it's our turn, we're maximizing. So that means the score for this board is +1, positive, because there is a way to guarantee a win, and it's this move that got us that positivity and the win. And so what Minimax will do after it does this kind of scoring is it's going to say, this is your move to make. It's a very simple example, but I think you get the idea, I hope. It's going to point to that one and be like, that is your move. Make that one, and you will have the best chance of winning. Okay? So obviously when the game is not this close to completed, there's no right answer, or there's no like obvious, you better take this move and you'll win immediately move. But sometimes there are better chances than others, because you're going to like average together things and make sure that you have the best possibility of winning. Okay, so that is Minimax in a nutshell. It is an algorithm to try and win a game, find the optimal strategy. Any questions about that? So let's keep on trucking. I have one last set of slides, just the start of it. Only about recursion is as far as we'll be able to get this semester due to the holidays. So let's talk about this cool concept called recursion. What it is you find problems and they live inside of themselves. You find smaller versions of the same problem that you're trying to solve inside of itself, which sounds very confusing the first time you see it, but it is kind of logical. And eventually that problem gets so small that you can immediately solve it, and then you can build it back up. So you can think of those Russian stacking dolls as like a recursion problem. That's essentially where I'm going with this. Got a biggest doll, then you can find a similar looking doll inside of that one, a similar looking doll inside of that one, on and on forever until you get to the smallest version. There's nothing inside of that. You can immediately say, I have an answer, and then you can start like building it back up to get to the original problem that you were trying to solve. So that's recursion in a nutshell. You can use it to solve many problems. But it is a kind of looping in that sense. It's repetition in a weird way, and you can use it, among other things, to solve for the optimal strategy to play the Tower of Hanoi game, if you've heard of that, where you're trying to like move the stack of discs to another peg, where you can't like put bigger discs on top of smaller discs. And so recursion is a very efficient way, or I guess it's the easiest way to find the right answer for that game, for example. It's a recursive problem, we say. That's the adjective. So recursion is when you have a problem and you're finding it inside of itself. All right? And so I guess let me read this first. You might be thinking, if you've never seen recursion before, like, isn't it just circular reasoning to like look for a problem inside of itself? It's like, all right, I'm trying to solve this problem. Oh, let me find that problem again and solve it. It's like, you'll never get anywhere. It just so turns out that if you do it right, you will get to an answer. And the key is that your problem needs to get smaller. You need to find a smaller version of the same problem. So like, here's your original problem. It's a box. You find a smaller problem, a smaller box inside of that box, and you solve that one. And then you can use that answer to build the solution for your bigger box, which looks different. That is the goal. All right, so recursion is all about solving a problem in terms of smaller versions of itself. And I'll give you a good example on the next slide. And so what you want to do when you're faced with a recursive problem is you need to notice it inside of itself. Find a smaller version of that exact same problem. It's called a subproblem. Find that subproblem, and then get that answer. It's a smaller problem. You're guaranteed to find that answer. Once you have it, use that subproblem's answer to solve the original largest problem, like the big box that you wanted to care about. So again, that's probably very vague, and we could use an example. So here's my good example for the day, the factorial of a number. So I claim that taking the factorial of a number is a recursive problem. All right, so that means, like, take an example like 5 factorial, remember that? So you've seen the symbols before, I hope. 5 factorial is 5 times 4 times 3 times 2 times 1. That's what 5 factorial is, mathematically. Can you find, does anybody see the smaller factorial inside of 5 factorial? I'll give you a minute if you don't see it, yeah.
4 factorial?
Good, yeah, so here is 4 factorial. Does everybody else see that? That's 4 factorial. I guess there's more than even that. If there's 4 factorial, that means there's 3 factorial too. But this is the next smaller one. You always usually want to look for the next smaller one, so that's good to notice that one. But there are, of course, all the other ones too. That's 4 factorial, so there's 3 factorial right here. Here is 2 factorial, and then I guess this is 1 factorial sitting there as well. So this is a weird thing. We found a problem. The factorial problem has smaller versions of the same problem inside of itself. Like take 4 factorial, multiply it by 5, and now you've got 5 factorial. It's kind of a surprising thing. We've never seen it before. That's so cool. So yeah, we noticed the smaller factorial inside of like 5 factorial, for example. We found the 4 factorial. 5 times 4 times 3. Let me write this better. It's supposed to be 5. 5 times 4 times 3 times 2 times 1. So there's our 4 factorial. And this totally generalizes. Like you take 7 factorial. 7 times 6 times 5 times 4 times 3 times 2 times 1. You see the next smaller factorial is still sitting there. There's 6 factorial. So this can generalize. That's really cool. So like 7 factorial is 7 times 6 factorial. 5 factorial is 5 times 4 factorial. And what is that but a smaller factorial problem? If only I could write smaller factorial finding problem. Which is beautiful. Smaller is key. All right. So we can generalize this, like 7 factorial equals 7 times 6 factorial. 5 factorial equals 5 times 4 factorial. Using that pattern, what is n factorial? Well, pretend like n is the 5. It's n times n minus 1 factorial. You see how I'm reading that? N times n minus 1 factorial. That's the key. And so that is... that's the thing that we want to notice, all right? We've just defined the factorial in terms of smaller factorials. N factorial, like the biggest n factorial, is equal to that n times a smaller version of the problem, n minus 1 factorial. And we call that general case that uses the smaller answer, we call that the recursive case of the problem. We do need one more case, usually, one more. Sometimes there's multiple other cases, but we need a stopping way. We need a stopping condition now. Because if you just kept following this rule, you'd never finish. Because it's always trying to hand off the problem to the next smaller factorial. And so in addition to the recursive case, we need a stopping condition called a base case. And that is when we immediately know the answer to a factorial problem. We don't have to do any smaller work. And so let's try and use our rule to figure out when we want to stop. So 5 factorial following this rule when n is 5, that's all right, that's equal to 5 times 4 factorial. What is 4 factorial? That's 4 times 3 factorial according to our rule. What's 3 factorial? That's 3 times 2 factorial according to our rule. That's still making sense. We still can do all that. What's 2 factorial? That's 2 times 1 factorial according to our rule, which I guess still makes sense. What's 1 factorial? That's 1 times 0 factorial according to our rule. That's starting to look a little fishy, but I guess you can mathematically define 0 factorial. It's mathematically defined to be the number 1, so technically you can go there. But if you go any further, like 0 factorial, according to this rule, that is equal to 0 times negative 1 factorial. And not only does negative 1 factorial not exist, but you've just multiplied your entire answer by 0 now, and so the whole thing's 0. So you do not want to get to there. Like the recursive case rule breaks down at that point, so we shouldn't have gotten there. And also, maybe you've never seen 0 factorial before, so we can just let's stop at 1 factorial. Does that sound good enough for us? Because this is a case where we immediately know the answer. Somebody asked me for 1 factorial, I do not have to do any more work. I don't have to compute a smaller factorial. I can just memorize that 1 factorial is 1, and just give back 1 whenever anybody asks me for 1 factorial, and then I can be done with it. So that's called the base case. 1 factorial, if somebody asks me for that, that's the small version of the problem. I immediately know the answer. I'll just give back 1 as the answer. And that's called the base case. That's your stopping condition that allows you to eventually be done with this long chain of unfolding your problem. That's like the smallest little doll that's stacking. Okay? So the recursive case and the base case together can now solve any factorial. Are there any questions about how we discovered that and why it makes sense? It's a very powerful concept for certain things. And so let's code this up now. The whole point of a recursive problem, in computer science at least, is like solving it somehow. So how do we translate these rules that we noticed to code is the next question. All right. So let's write we're asking for the factorial of a number. So let's write a function that's going to give back the factorial. Let's make it a recursive function that computes that factorial. All right. A function is usually the unit of code that you can make recursive. And the idea is we have to ask for a smaller factorial. And we're gonna write a function that's meant to return the factorial. It's meant to give back a factorial. And so asking for a smaller factorial inside of the definition for a factorial for a function means that our function that we're writing is going to call itself as it's working on smaller inputs. That's just because the problem is defined in terms of itself. That's how it works. Let's make our function be called fact. And so we're going to ask for the fact of 5 to go off and compute 5 factorial. It needs to go off and ask for 4 factorial because that's what we noticed needs to happen when we're asking for 5 factorial. We're going to multiply 5 times 4 factorial, which means that this computation is going to go off and wait for fact of 4 to give back an answer, which is kind of cool. Which is then going to go and call fact of 3, fact of 2. It's all going to unwind. It's going to be cool. I'll show you some diagrams. But here's the function that's going to do this. We're going to call it inside of itself. So def fact of n, and it's meant to give back the factorial of n. So computes n factorial. What do we do in the factorial function? We go and implement these two rules. So we have to use an if statement to determine whether we're in the base case or the recursive case. We know we're in the base case when our input is 1. So if, and n is called, the input is called n. If n is 1, then that means we're in the base case. And somebody asked for 1 factorial. And we have defined 1 factorial to be just 1. Just give that back. We're ready. So return 1 to whoever was asking for it. And we're done. Otherwise, else, we must be in the recursive case. So we need to go off and give back n minus 1 factorial times our n. So if it's 5, our 5 times factorial 4. And so we have to go off and compute the factorial of the next smaller number. We have to call fact of n minus 1, because we're n. We're going to go off and compute fact of n minus 1. We can save that somewhere in an x variable. And we return, our final answer is that times our current n. So return n times x, because x was the smaller factorial. And so here, we went and asked for a smaller answer, which is so cool. It's going to work. Are there any questions so far about how to translate the rule that we noticed into code? You see how you can kind of just read it off? This is what it's got to be. It's weird, though. It should make you feel uneasy that we're calling the function that we're defining inside of itself. But because it's on a smaller input, it's eventually going to get down here and build itself up. It's going to work. So I will now be able to call fact of 5, for example, and it's going to go off and compute an answer. Print fact of 5. That really will go and give back the answer, which is apparently 120. Let me show that to you. Let's see here. Let me just open up idle, I guess. That's what I need to be doing. And what lecture? We were lecture 29. Did idle open or not? I can't tell. There it goes. So we're lecture 29 today. and I'll call this facts. That's the name of our function we're about to write. So let's at least attempt to get all this on the same screen. There we go. So, okay, factorial function. Computes n factorial def fact of n if n is 1. That is our base case. And we return 1. Somebody asked for the factorial of 1. Otherwise, we must be in the recursive case. And we need to go off and compute the factorial of n minus 1. And the answer is Rn times that. And it really is going to work. So print fact of 5 really will give back the right answer. It is the 120. And you can do this for any factorial that is like non-negative, because those don't exist. Factorial of 3, that's 6. And it will go off and figure that one out too. Those two rules, it doesn't look like it, but they are able to compute any factorial. That's so cool. So that's the code. Any questions yet? Still doing good enough? So I want to draw for you why it's working, and hopefully it'll make a little bit of sense. So I want to draw a diagram for you called a stack diagram. And it's going to show the way that the factorial function is calling itself on smaller inputs and how it's unwinding all of those calls to a final answer. And that should hopefully help. So this thing is called a stack diagram. And I'm just going to draw a bunch of things on top of each other. And you think of it as a stack of work. A stack of work to be done. Like a bunch of papers on a desk. Stack of work to be done. And then also, it will also tell you who wants the answer for whom. So, who wants the answer? Who wants whose answer? And it'll just be the person below you on the stack who's asking for your answer. And so this will make sense when I draw it, but all right, here's our code. We called, let's say that we're trying to figure out what's going on with this call to fact. So we're trying to print fact of 5. So at the outermost code, we're calling print fact 5. Print fact 5. So that's like a piece of paper that remembers that we're trying to do that we add to our stack of work to do. And then, well, we see that print needs to print something. It doesn't know what to print yet. It needs to print whatever the fact of 5 is, and that needs to be computed still. So we have to go off and ask for, like print needs an answer, so it's going to go off and ask what in the world is fact of 5. I need to print that. And you can see how, like this is the new piece of paper that's like the next work to do. You can see how the person who wants the answer is the person immediately below it on this thing called the stack. That's why the diagram is a nice thing. And so fact of 5 gets made, and then we're inside of the fact of 5 function. So we're called here, n is 5. It's not 1, so we're not in the base case, but we are in the recursive case. And so what we do is we have to run these two lines. We have to make an x variable, and that will belong to this call to fact. It's a local variable to the function. Let's draw it like that. And we need to fill in with the fact of n minus 1, which is something we don't know yet. n minus 1 is 4, but we don't know what the fact of n minus 1 is. We have to go off and compute that. So this call to fact is going to be waiting right here in this line. It needs to go off and ask for fact of 4. It needs to go off and call itself fact of 4. Does that make sense? So fact of 5 is waiting on fact of 4 now, because it doesn't have an answer ready yet. And so now we're in fact again, but n is now 4. There are 2 calls to fact that are not done yet. That's the tricky bit. And again, that's going to hit the recursive case, and so that's going to make its own x variable. It's like, all right, I need to fill that in because I need to go off and compute the fact of 3, which I don't immediately know, so I need to go off and ask that of myself on a smaller input. So fact of 4 is going to go off and call fact of 3. And so now there are 3 calls to fact waiting to be done, left to do. So fact of 4 and 5 are waiting on this line still because they need to know that smaller factorial to like continue. They're all waiting right now. Everybody below is waiting for the person on top. So now we're in fact of 3, n is 3. Again, it's not 1, so we're in the recursive case again. It needs to make its own x variable because it needs to go off and compute fact of 2. And I think you see the pattern now. Fact of 2, again, is the recursive case. It's trying to compute fact of 1. You go and ask for that, fact of 1. And that one, we call fact of 1. Like, first of all, there's 5 factorial calls just still working. They're all running at the same time. It's fact of 1's. We're working on that one right now. But everybody underneath is still waiting. It's still has stuff to do. So now we're in fact of 1, and we're finally in the base case. So n is now 1 for this particular call, and it returns 1 to whoever called it. And so the person below you on the stack, that's why the diagram is nice, is who you want to give your answer back to. It's who's waiting on you. So fact of 2 is waiting on fact of 1, and it has an answer to return. It's going to return 1 to who called it. And that was fact of 2. And so now fact of 1 is done. It's returned. I should erase it, but I'll keep it here just so that you can study it later. But fact of 1 is now returned back to fact of 2, who was waiting right here on fact of 1's answer to put into its x variable. Now it has a 1 to do that. I can put it in its x variable. Now fact of 2 is done, because it can return its n, which was 2, times the 1 that it got back and put in x. And so it's going to return the number 2 to whoever called it. And that was, again, the person below it on the stack. Fact of 3 was waiting on fact of 2. It's done. It's returned. So now we're back in fact of 3, who was waiting on this line for fact of 2. Now it's finally done. So I got the 2 back. It can place that in its x variable and multiply its 3 by that 2 to give back its answer. And so that creates 6, of course, and that is the correct factorial of 3. And it's going to give that back to whoever called it. Do you see how that's all unwinding? Is there any questions about that? See how kind of the code is modeling the diagram, or vice versa? This is what I want you to understand. This is the key to see it work. You see that everybody's going to give back the right answer, and it's being built up slowly once you get to the base case. So now fact of 4, who was waiting here again to fill in its own x for fact of 3, it got back fact of 3, that was 6, you can put it in its x, and now it's ready to return its n, which was 4, times x, 24, back to whoever was calling it, and that was fact of 5. Gets the 24, finally, was waiting on this call, took a very long time, but now it has the answer, back from fact of 4, that was 24, place that in its x, and its job was to take that smaller answer and build up the bigger answer for the original call to fact of 5. Using fact of 4, now it has it, can multiply its 5 by 24 and give back its answer to whoever was waiting on it. The answer is 120, apparently. And, sorry, we were back in fact of 5. And then it's done. It gave back that answer to whoever was calling it, and that was print. And now print has a real number to go and print. And so on the screen is when it will show 120, and now print is done. That is how this is computing the right answer. That's how it's getting down all the way to the base case and building the answer right back up and using the recursive case rules. Are there any questions about that? That is a tough concept for sure, but it is a powerful one. You will see it again if you take another programming class. All right. So yeah, that is as much as I would like to melt your brain this semester. That is everything that I have for today, and then no new assignments from now on. That would be evil because we only have 1 week of classes left. So next week will just be review, and I'll just talk about stuff you already know. So this was the last new concept, and the rest of the time is yours to work.